Okay, we'll see if this series converges or not, and I think it's a good idea to put this into a sigma notation, so let's go ahead and do that. Well, everybody has a 1 on the top, so this is the sigma when n goes from 1 to infinity. We have 1 over, and notice on the bottom, we go from 4 to 7, 7 to 10, 10 to 13, and 13 to 16, and so on. Every time we just add 3, so that's the common difference. That means that's the coefficient of n. We have 3 times n. And now we have to figure out what to add right here. Well, when n is equal to 1, 3 times 1 is 3, plus what will give us 4? Well, just add 1 to it. So this is the formula for the terms, and we have the series right here. And you see, this is really close to the summation when we go from n from 1 to infinity of 1 over n to the first power. Let's just do a limit comparison real quick. So let's go ahead and put down what we know. We know the sum as n goes from 1 to infinity of 1 over n to the first power. This right here is the harmonic series. So we know it diverges, but you can also say p is 1, which is less than or equal to 1. Therefore, by p series, it diverges. Then we can just do the check. And this right here, let's do the limit comparison test. So to do that, I will just take the limit. You can just write down as limit as n goes to infinity. You don't have to write down the LIM. This is legit as well. Put down the one that we're trying to do on the top, and not a summation, just the function, just the sequence formula part, right? 1 over 3m plus 1, and divided by, put down the one that we know on the bottom, namely 1 over n, and do the algebra. So that's just multiply the top and bottom by n, so they cancel. Put down equal sign because we're just doing algebra, and you see this is just n over 3m plus 1. And now let's do the limit. As n goes to infinity, well, this is n to the first power, this is 3n to the first power. The plus 1 doesn't really matter, and we can just draw arrow, and the limit for this is just 1/3. And now, when we do the limit comparison test, does 1/3 do us any good? Yes, it does. And you have to know, you're looking at 1/3 and compare this with what? Compare this with 0. This is greater than 0. For limit comparison test, we're using 0 to help us out. This is a positive finite value, so we know we can draw a conclusion. And the conclusion is that, well, this and that will have the same conclusion. This right here diverges. This right here also diverges. So let's just go ahead and write this down. The sum as n goes from 1 to infinity, 1 over 3m plus 1, also diverges. And this time, we did the limit comparison test. So by the limit comparison test. Let's go ahead and put this into the sigma notation, shall we? So here we go. The sum as n goes from 1 to infinity. Everybody has a 1 on the top, so we have a 1 over. And for the bottom, we see that we have 3, 6, 11, and so on. Every time, you see that this right here, we add 3, but next one, we add 5. And the next one we add 7, and the next one we add 9. Well, the first level is different, but if you look at the second level, every time we add 2. So you can suggest, you can kind of be suspicious that this is a quadratic. Well, I think it's a good idea to look at the perfect squares. Well, remember, 1 square is equal to 1, 2 square is equal to 4, 3 square is equal to 9, 4 square is equal to 16, and so on. And if you look at 1 compared with 3, 4 compared with 6, 9 compared with 11, yes, you just add 2. And the next one, 5 squared, right? You get 27. So all in all, this is just n squared plus 2. That will be the formula for every term, and we're adding things up. Now, how can we do a comparison? This time, you have 2 ways. You can do a limit comparison test, or you can just do the direct comparison test. Both of them will work. So let me just show you guys both for practice purpose. First of all, let's put down what we know, namely just 1 over n squared, the series for that, right? So the sum as n goes from 1 to infinity, 1 over n squared. We know that by the p series, his p is 2, which is greater than 1. That means this right here converges. Okay, here is the check. And suppose we are doing the direct comparison test first. So I'll just put down this is the DCT test. To do so, we put down the one that we're trying to do on the left-hand side. And again, this is just for consistency purpose. And of course, we can put down the one that we know on the right-hand side. And you can kind of see this is true already because the bottom is bigger than this. That means the whole thing is smaller than that. But if you just want to practice this, then I think this is a good format for you to practice. So you want to show this is less than or equal to. Remember, for direct comparison test, we are trying to compare this by using inequality. This is a convergent. We want to show that this right here is smaller than convergent, so we can draw conclusion. And notice everybody is positive because you add, and then also n is positive and all that. So everybody will be positive right here. So that's the good thing for that. Anyway, notice that this is just 1 over n squared plus 2 on the bottom. So just compare the formulas right here, right? And just take away the summation. We have this. And we are trying to see if this is true or not, but this is so clear. If you cross multiply, this is even better. Cross multiply, you get this. This is so true. Seriously, right? Anyway, this right here is so true. So right here, if you would like, you can just draw your conclusion already. And you can say the one that we are trying to do, let me just see the sum n goes from 1 to infinity. 1 over n squared plus 2 also converges. And if you do it this way, you quote by direct comparison test. And that will be it. Well, some people don't like the direct comparison test sometimes. Well, I will also show you guys how you go check if you do the limit comparison test. Limit comparison test. For the limit comparison test, of course, you take the limit. So first of all, I will just put down, well, that's as n goes to infinity. And put down the 1 that we're trying to do on the top. 1 over n squared plus 2. And put down the 1 that we know on the bottom. And again, we're just comparing the formula. That's the idea right here, right? Okay, then let's see, do the sum algebra. Let's just multiply the n squared on the top and bottom so that this and that will cancel. This is just n squared over n squared plus 2. Then can we take the limit? Yes. As n goes to infinity, just care about this and that. And now I will draw arrow because we are taking the limit. And it's just 1 over 1 right here, right? N squared cancel, it's just 1. Now, be careful with this one. How are we going to use this one? Remember, for the limit comparison test, we are comparing the limit, look at this limit, right, with 0. This is a positive finite value. Then we can draw a conclusion. This is greater than 0. We draw a conclusion. The conclusion is that the one that we're trying to do and the one that we know, they have the same convergency. This converge, that one also converges. So let's draw the conclusion. The conclusion is the one that we are doing, which is this, also converges. And if you do it this way, you quote by the limit comparison test. We'll first take this and put it into the sigma notation first. So let's go ahead and make that happen. This is when n is equal to 1 to infinity. All right, everybody on the top is 1, 2, 3, 4, 5, and so on. So as n goes from 1, right? So we just have n on the top. But on the bottom, we see that this is like 1 over 1, if you like. Yeah, 1 over 1. And then this is 9, 25, and 47, 81. What do this number remind you of? Perfect squares. But not all the perfect squares. So, because this right here is only what? This is only 1 square, and the 9 is 3 square, and 25 is 5 square, and then this is just 7 square, and this right here is 9 square, and so on. So we only have the odd numbers, and we square that. So look at the numbers in pink first. We'll write the formula for that, namely just the odd numbers. Not so bad. It's just 2n because they are off by 2 every single time. And we use n is equal to 1, and just do a quick check. 2 times 1 is 2, and we have to minus 1 in order to get to this one. So we have 2n minus 1 in the parentheses. And you can see if n is equal to 3, you put it here, you will get 5 right here. So that's pretty much the idea. So this is what we have, and don't forget that we have to square this. So that's it. And now, does this converge or diverge? Well, if you would like, you can also work out the bottom a little bit, because expand this so that we can pick up the powers easily that way, right? So let's go ahead and do that. The limit as n goes from 1 to infinity. On the top is just n over, you multiply this out. So you do this square, 2n squared with the 2, okay? So it's 2 squared, which is 4, and then n squared, so we have 4n squared. Then 2 times this and that will give us a total of minus 4n. And lastly, you add the square of 1, which is just plus 1. So just multiply it out, or like use the formula to work it out. Now this is what we have. What do we know? If you just compare this and that, yeah, we can use a series that we know much better. So let's go ahead and do some comparison. Well, let's look at the sum as n goes from 1 to infinity. If you just picked up n and 4n to the second power, you have the detail 4 on the bottom. That's fine. But if you just picked up n over n squared, that's just 1 over n. You can do this as well if you would like, right? So let's just put this down. And this is like the harmonic series. Of course, you know this right here diverges. Or you can also say that p is equal to 1, which is less than or equal to 1. Therefore, it diverges. All right, here is the check. Well, as you can see, on the bottom right here, you have 3 terms. Maybe you can still work out the direct comparison test by doing some algebra with inequality. I'm going to leave that to you because I like to do limits sometimes. So in this case, what I will do is I will check as n goes to infinity, and we are doing the limit comparison test right here. Well, put down the one that we are doing, which is just the formula, which is n over 4n squared minus 4n plus 1 divided by the one that we know. Again, just put down the formula, which is the 1 over n, like this. Now do some algebra, multiply the top and bottom by n, so that this and that will cancel. This is just algebra, so put down the equal sign. Then you see this times that, we get the n squared over, this is 4n squared minus 4n plus 1. Now, take the limit. Well, on the top we care about this, on the bottom we care about this. This right here will go to 1 over 4 because they have the same degree, so this is 1 over 4. Okay, can we use this result? Yes, and remember, you are looking at this limit and you have to say this is greater than 0 for the limit comparison test. Now, let's go ahead and put this down. Here is our conclusion. And the conclusion is the one that we are trying to do. You can put down whichever one that you want. Let's just put on this one. So the one that we're trying to do, which is the sum as n goes from 1 to infinity, n over, let's just put this down right here, why not? Minus 4n plus 1. This right here also diverges, right? Because they have the same conclusion. Also diverges, and we did the limit comparison test. So that's it. And remember, here's a quick idea. The reason that this works, you can just think about the following. Well, you will compare the formula, the sequence formula, right? The an parts, and then also the bn part. And we took the limit, and we found out this is about 1 over 4. This means this guy is about a quarter of the size than that. And this right here diverges to past the infinity, which implies that this right here, it's just about a quarter of that infinity. A quarter of that infinity is still infinity. Therefore, this right here also diverges. First, if you take the limit of just the formula, sine of 1 over square root of n, this right here does go to 0, but it does not tell you if the series of this converges or not, okay? Well, in this case, let's again try to do some comparison, and it seems that we have this function part right here, right? The formula is just 1 over square root of n, not the function, but that sequence part. Well, let's go ahead and try that. Let's put down what we know. And this one is also pretty straightforward and goes from 1 to infinity. Ignore the sign. We just have 1 over square root of n. And of course, this is the same as the sum and goes from 1 to infinity. 1 over n to the 1/2 power. Okay, here the p is equal to 1/2, but this is less than or equal to 1. Therefore, this right here diverges. Okay, then let's go ahead and do some comparison. Let's do the check. For this one, we have sign. I don't think it's a good idea to do direct comparison because inequality might not work out easily. It's a much better idea to do some limits. So let's go ahead and take the limit as n goes to infinity. Put down the one that you are trying to do on the top, namely sine of 1 over square root of n, and divide it by the one that one that we know on the bottom, which is this. Let me use the square root as well. Okay, if n is going to infinity, put it here, you will have sine of 0 over 0. But don't worry, this is from one of the limits. The limit, actually. The special case, the one that you should know. The secret weapon, right? So this is how you can do it. I will actually draw some equal sign to show you guys the change of variables. Right here, I will just take theta equals the input, which is 1 over square root of n, like this. And when theta is equal to square root of n, notice that if n goes to infinity, that means theta will go to 0. Yeah? So you're looking at this as sine of 1 over n is just the theta, and the bottom is just the theta, and this right here will go to 1. Because this is the limit. This is 1. And now, how can we use this one? Well, 1 is greater than 0 because we are looking at this as the limit comparison test. 1 is greater than 0, and it's good because we can draw a conclusion. The conclusion is this and that, well, this one diverges, that one also diverges. So let's go ahead and put that down. Here is the conclusion. I will just write down the sum. N goes from 1 to infinity. Sine of 1 over square root of n also diverges. And the reason is because we use the limit comparison test. Yes, we are in the limit comparison test section, or maybe the direct comparison test section. But in this case, don't do any comparison. If you do comparison, in fact, you end up with a really bad answer because it's not correct, of course. Anyway, here is the deal. Remember, cosine of 0 is actually equal to 1. This is what we are going to do. Let's go ahead and do the check. Right here, I will just take the limit. And I know sometimes I put down as n goes to infinity, sometimes I put down lim, but one or the other doesn't matter, okay? Take the limit of the formula an right here, namely cosine of 1 over n squared. And now if you put infinity to here, well, we just get cosine of 1 over infinity squared. And you can just draw a conclusion because the bottom is infinity, and 1 over that is 0. And you have cosine of 0. This right here actually goes to 1. So let me just show you. This is cosine of 0, which just goes to 1. That means this right here is equal to 1. And this time, we're using 1. And we have to remember, this is not equal to 0. Because what we did is, we look at this only and take the limit as n goes to infinity. Well, we end up with 1, which is not 0. And we are doing the test for divergent. It helps us out. Therefore, we can say the conclusion, the one that we were doing, which is that the sum as n goes from 1 to infinity, cosine of 1 over n squared, this right here, diverges by the test for divergence. Okay? So, again, do not do any comparison test whatsoever. This is it. Of course, as I told you guys, you should always check the limit of this, right? And if you don't end up with 0, that's a good news because this time, we end up with 1, which is really good. We get to draw a conclusion by the test for divergence. Sine, okay? N goes from 1 to infinity. Sine square of 1 over n. Here, you might want to use the 1 over n as well, but this is sine square. The truth is, we actually have to use 1 over n squared, right? The series for that. So let me show you. We actually know the sum as n goes from 1 to infinity of 1 over n squared. This right here, how many times have we used it? A lot, right? So better make sure that you get this right. This right here converges. And then we are going to check as n goes to infinity. This is not bad because I hope we can use the best friend. Well, I mean we can actually use the limit. You'll see. Put the 1 right here on the top, sine square of 1 over n, over this on the bottom. This is why we use 1 over n squared, because you know sine square is the same as saying sine of 1 over n times sine of 1 over n. And of course, I can write this as 1 over n times 1 over n. Everybody happy. And of course, if you want to really quote the limit, to quote the limit, you can just say let theta equals 1 over n. So theta goes to 0. And this right here becomes sine of theta times sine of theta. And we have this divided by theta, divided by theta. And this right here approaches 1 and 1. Of course, in the end, this is just 1. So again, this is also useful. This is greater than 0 is useful. Come back here, draw the same conclusion because this is greater than 0. If you just use 1 over n, it's not good, right? And this right here also converges. Why? By the limit comparison test. LCT. Of course, we can just go ahead and pick up this and that, and we can come with something that we know much better, right? So let's go ahead and do that, and let me write down what we know. And that's just the series as n goes from 1 to infinity. N to the third power over n to the fourth power is just going to be 1 over n to the first power. With this being done, we know that p is equal to 1, which is less than or equal to 1, and this right here diverges. Or you can also say the harmonic series diverges. Okay, so now let's build out a connection between this and that. There are two ways to do it, either the limit comparison test or the direct comparison test. Up to you. In this case, both of them will work out nicely. So perhaps let's do the direct comparison test right here. And I'll also show you guys a limit comparison test later. For the direct comparison, put down the one that we're trying to do on the left-hand side. N goes from 1 to infinity. N to the third power plus 1 over n to the fourth power plus 1. And put down the one that we know on the right-hand side. Again, this is just for consistency purpose. And 1 over n to the first power. Now, this right here is a divergent series. And we're trying to show that this right here is bigger than the divergent so that we can conclude this right here also diverges. So be sure you set out this inequality this way. But I don't know if this is true or not yet, so put down a question mark. And notice that everybody right here is positive, so just make a little note right here. Okay, now let's just work out the formulas. Right here, this is n to the third power plus 1 over n to the fourth power plus 1. Is this greater than or equal to 1 over n to the first power? And we are looking for when n is 1 to infinity, so when n is greater than or equal to 1. All right, so let's go ahead and cross multiply because everybody is positive. So this times this, we get n times n to the third power plus 1, and this times that. Is this greater than or equal to this times that, which is n to the fourth power plus 1. And of course, you can distribute this real quick, and we see this is n to the fourth power plus n. Is this greater than or equal to n to the fourth power plus 1? Yes, it is, because of course you can just minus n to the fourth power on both sides, so they cancel, and here we get n is nicely greater than or equal to 1. And we go from 1 to infinity, so this is really nice. So this right here is nicely true, and finally you can draw the conclusion. And the conclusion is that the one that we're trying to do, which is the sum, n goes from 1 to infinity, n to the third power plus 1 over n to the fourth power plus 1, also diverges, because that one was a divergence integral. This is bigger, this is also divergent, and here we did the direct comparison test. And that's it. Don't go yet, because I can also show you guys the limit comparison test. So maybe you would like this one, and if you check out this one, maybe you like it more. So we'll see. For this one, limit comparison test. And to do so, first we take the limit. So let's just put down as n goes to infinity. And then put down just the formula part, right? The one that we are trying to do right here on the top. We see that this is n to the third power plus 1 over n to the fourth power plus 1 divided by the one that we know, again, just a formula, which is the 1 over n to the first power, like this. Okay, so to simplify the complex fraction, we'll just multiply the top and bottom by n. This and that will cancel nicely. And of course, don't forget that this is like a parentheses and just distribute the top. Equal sign, because we're just doing the algebra, this times this is n to the fourth power plus this times that, which is n, over the denominator, like this. And then we take the limit, and notice that we have a rational expression here. So to take the limit, just pay attention to the highest power, which is n to the fourth power. And this is also n to the fourth power. Therefore, this right here will approach 1, and that's the limit. And this is so nice because when we are doing the limit comparison test, the 1 will tell us some conclusion. Because this 1 is bigger than 0, that means the 1 that we are trying to do has the same conclusion as the 1 that we know. This right here diverges, therefore this right here also diverges. So let's draw our conclusion. And let me just write down the sum as n goes from 1 to infinity, n to the third power plus 1 over n to the fourth power plus 1. This right here also diverges. And if you do it this way, be sure you quote by the limit comparison test. And with that, we are done. Let me know which one do you guys like more. Here's the deal. Let's go ahead and just consider the series of this over that. And in fact, notice that the top is 3 times n that we just circled it. In fact, you don't have to include the 3. It's just a constant multiple. So it's okay if you just look at this as n over that. So it's kind of up to you. When you have a constant multiple with a divergent or a constant multiple with a convergent series, it's still the same conclusion anyway. So let me just not include the 3 if you don't want to. So right here, let's go ahead and put down what we know, which is the sum as n goes from 1 to infinity. Let me just write down n over, this is the square root, and let me just put the square root in red, and then we have n to the fifth power. Again, the constant multiple 3 doesn't really matter. So right here, let's go ahead and simplify this a little bit, because this is the series as n goes from 1 to infinity. This is n over, this is the same as saying n to the 5 over 2. The index right here is 2. So this is the exponent for that, and this is 1. So of course, we have to simplify the exponents right here. And of course, let's just do that real quick. So you just do 1 minus 5 over 2, which is going to be negative 3 over 2. And again, that's going to be the new power for n. That's n to the negative 3 over 2. So it will go down to the denominator. So this is the series as n goes from 1 to infinity, 1 over n to the 3 over 2. Just fraction anyway. Well, once we have this, look at the power here. Now p is equal to 3 over 2, which is greater than 1. That means this right here converges because we're using the p series, right? This right here greater than 1, so it converges. Then we are going to do the check. And here is my recommendation. As you can see, this rational expression is pretty crazy. So in that case, it's a good idea to do the limit comparison test so that you don't have to do too much with the algebra with the inequality, all right? So I will just use the limit comparison test. Easier to say. All right, so here we go. I'm just going to say we'll take the limit as n goes to infinity. Put down just this expression on the top, which is 3n plus 1 over square root of n to the 5 plus 4n squared plus 12 like this. And then divided by, that's put on that, which is 1 over n to the 3 over 2 power like this, right? Then, of course, let's just do some algebra, which is just multiply this guy on the top and also on the bottom. So that's pretty much the idea. So this is n to the 3 over 2 power. They cancel nicely. Now, we see that we just multiply this and that. So this times that, we get 3n. And of course, we add the powers. This right here is first power, and this times that. 1 plus 3 over 2 is going to be 5 over 2. And then this times that, which is just, this is self n to the 3 over 2 power. And then divided by that, which is square root of n to the 5 plus 4n squared plus 12 like this. All right, let's go ahead and take the limit, and this is all we have to do. So all these terms right here, they're just x to some power, n to some power. And when we have this situation, just compare the highest power of the n on the top, which is this, and also the highest power of n on the bottom, which is this. You guys can actually see this right here nicely. This right here, well, we'll take the limit, so I shall draw arrow, and then we pretty much have this over that, which is 3 to the n over 3 times n to the 5 over 2 over this, which is the same as that. That's also the same as n to the 5 over 2. And this right here will go to 3, of course. And because we're doing the limit comparison test, this is good. And notice we are looking at this, and we have to say, this is greater than 0. And this is greater than 0 means that we get to draw a conclusion right here. This has the same conclusion as that. So I will just put this down right here for you guys. Here we conclude that the one that we're trying to do, which is the series as n goes from 1 to infinity over square root of n to the 5 plus 4n squared. Just write down the original question again, pretty much. This right here also converges, and the reason is what? Because we did a limit comparison test. Yeah, there we go. Man, this is not rational expression though, so let's see. First of all, we have the nth root of e. That's kind of weird. Well, we don't like to look at the radicals as radicals in calculus. We like to look at radicals as power, right? So let's make some change first. So this right here is the series as n goes from 1 to infinity. And whenever we have whatever root, whatever radical right here, in this case it's the nth root. This right here is going to give us 1 over n power. So the base right here is e, and then we have to raise that to the 1 over n's power like this, and then minus 1 like that. Okay, here is a real quick check. Well, look at this expression. Let's try to do the test for divergence. So again, this is just the test for divergence. Meaning that, let's go ahead and take the limit as n goes to infinity. And I know sometimes I put down LIM, sometimes I put down as n goes to infinity, but you should know both, doesn't really matter. Anyway, let's put this down, which is e to the 1 over n minus 1. All right, let's put infinity to here. This is going to tell us we have e to the 1 over infinity. Let me just write it down like this. And then minus 1. 1 over infinity is what? 0. And e to the 0 is just going to be 1, isn't it? So this is just 1 minus 1, which will end up with 0. Man, again, when you are trying to do the test for divergence, if the limit of this, which is the an right here, is equal to 0, unfortunately, we cannot draw any conclusion. All right, it's okay though. Don't worry too much. I'll take care of you guys. All right, let's do some comparison business, of course. Because I noticed that, in fact, notice we have the 1 over n here. It's really weird. We know that if we just have the series as n goes from 1 to infinity of just 1 over n without anything else. This right here, of course, as we all know, this is the harmonic series, but let's just write this down. P is equal to 1, which is less than or equal to 1. And we know that this right here will diverge, right? The P series or the harmonic series when P is equal to 1, that's the case. How can we make a connection between this and that though? Well, let's do some comparison, right? And here is the deal. Let's go ahead and do the check. By the way, I forgot to draw the sad face. There we go. Anyway, do the check. We have two checks. One is with inequality, the other one is with limit. And if you see this part, if you want to show this is like greater than that, I don't think it's easy. I don't think it's easy to deal with inequality. So let's do limit. So let's go ahead and use the limit comparison test, right? And with that being said, let me just go ahead and write this down. We just will take the limit as n goes to infinity. You see, right here I put down n goes to infinity. It's the same as this idea, right? So just get used to the notations, all that. And then put down the one that we're trying to do on the top, which is e to the 1 over n minus 1. And put down the one that we know, again, just a formula on the bottom, like this. Okay, so, let's see. Well, again, if you put down infinity to here and here, we will get 0 over 0. That's no good. But it's actually good because we get to use L'Hopital's rule. However, do not use L'Hopital's rule in the end world. We have to change to x, right? So let's go ahead and just check this one instead, right? So let me just write down e to the 1 over x minus 1 over 1 over x. And then we do L'Hopital's rule, d dx, right? d dx. And again, this is as x goes to infinity, of course. All right, here we go. Derivative of e to the 1 over x, well, the function part right here repeats, so we have e to the 1 over x. Then we multiply by the derivative of this, right? Because of the chain rule, multiply by the derivative of 1 over x. Namely, we get negative 1 over x squared. And then the derivative of negative 1 is 0, so that's it, divided by the bottom. When we differentiate this, we nicely get this right here as well. So we have negative 1 over x squared. And nicely enough, these guys, they cancel each other out completely. So we end up with just e to the 1 over x, right? And then we will just take x goes to infinity. So we just put this down right here, e to the 1 over infinity, which is 0. E to the 0 is just going to be 1. So let me just write it down. And this is 1. For the function part, if a limit exists, that means we can show that this right here for the sequence, this right here also goes to 1. And for the limit comparison test, this is good. Again, 1 is greater than 0. Therefore, we get to draw our conclusion. So for the test for divergence, it didn't work. We'll just erase that and pretend that it didn't happen. And right here, we'll just go ahead and write down our conclusion. And the conclusion is the one that we're trying to do has the same conclusion as that, namely also diverges. So let me just put it down. Sum as n goes from 1 to infinity, and we have the nth root of e minus 1 on the outside. This right here also diverges, and the reason is because we did the limit comparison test like this. We have the sum as n goes from 1 to infinity of 1 over square root of 4 to the nth power plus 1. And apparently, this is the only part that we have at the end. The plus 1 usually don't matter, right? So it's a good idea to just ignore that and see what kind of series that we come up with, and that will be the ones that we know. Hopefully, we can draw a conclusion on that one nicely. So let's put down the one that we know, which is the sum as n goes from 1 to infinity. And again, just look at 1 over square root of 4 to the nth power. And of course, let's do some power business and all that. One of the power rule is, well, rule of exponent is that this right here is to the 1/2 power, and you can actually do that to the number first. So this is actually the same as saying square root of n equals to the sum as n goes from 1 to infinity. And let's look at this as 1 over square root of 4 and then raised to the nth power. Because it's to the 1/2 power, and you can just kind of do the 1/2 power first to the 4 and then the n on the outside. Anyway, of course, square root of 4 is 2, so this is the sum as n goes from 1 to infinity, 1 over 2 to the nth power. And this right here is what kind of series? It's not, this right here is not P series because you have the 2 as the base and the n in the exponent. So this is a geometry series. So what you can do is you can just rewrite it if you would like. Sum as n goes from 1 to infinity, parentheses, 1/2 inside to the nth power. Notice this right here is our common ratio. You can just put on r. In our case, it's 1/2. And if you're using the common ratio for the geometry series, well, absolute value of r, which is still the same thing, but be aware sometimes you may get negative numbers. This right here is less than 1. Absolute value of r is less than 1 means this right here converges for the geometric series, right? So I'll just write the for you guys. This is the geometry series test, right? So that's good because again, this is something that we can draw a conclusion rather quick. Then we are going to do the check, all right? And you can do the direct comparison test, or you can also do the limit comparison test. Up to you. Both of them will work. First, I will show you guys the direct comparison test. right? Because both works, I'll just show you guys for practice purpose. Well, with that being said, let's put down the one that we know, which is the one that we're trying to do right here, which is this 1 over square root of 4 to the n plus 1, and put down the one that we know on the right-hand side. So we have, let me just put down square root of 4 to the n, so they look the same. This right here is a convergence, so we wish to show that this right here is less than or equal to a convergence, so we can draw a conclusion. And again, everybody is positive, so that's great. Now, just compare the formulas. Here we have 1 over square root of 4 to the n plus 1. Is this less than or equal to 1 over square root of 4 to the n? Yes, it is. Yeah, but if you just do the cross multiplication, this times this is square root of 4 to the n. Is this less than or equal to? Put it here. Yeah, it's really clear now, right? So this right here is true. And congratulations, if this inequality is true, we get to draw a conclusion. And the conclusion is that the one that we are trying to do also converges. So let me write it down right here for you guys. 1 over square root of 4 to the n plus 1 also converges. And this right here, we did a direct comparison test. And with that, we are done. Some people don't like to do the inequality. In that case, go ahead and do the limit. Here is the check if you are doing the limit comparison test. And here we go. We'll still do that, right? So for the check, we take the limit as n goes to infinity, and we put this on the top and down the bottom, again, just for consistency purpose. So we have 1 over square root of 4 to the n plus 1 over 1 over square root of 4 to the n. Well, right here, let's just multiply this guy on the top and on the bottom so that we can simplify this real quick. And this is just square root of 4 to the n over square root of 4 to the n plus 1. And now, check this out. As n goes to infinity, on the top, of course, you have this. On the bottom, the dominating part is 4 to the n, but that's in the square root, so you have to worry about that. And in fact, yes, they'll just be approaching 1. And this time, you're using this 1. And how are you going to use it? Well, remember, for the limit comparison test, this is the limit comparison test. 1 is good because it's greater than 0. That means we get to draw a conclusion. And again, the conclusion is that the one that we're trying to do also converges as the one that we know. So let me just put this down. Here is the conclusion that we can make. The conclusion is the one that we are doing. 1 over square root of 4 to the n plus 1 also converges. This time in blue, we did the limit comparison test. Just like that. Now, look at this. You see that both of them works, right? Both of them work this time. However, imagine that if the question was square root of 4 to the n minus 1 on the bottom, in that case, unfortunately, the direct comparison test wouldn't work because you will have a minus 1 right here, and that inequality is not true anymore. But the limit comparison test will still work because, again, when you're adding something that's not that important compared to the dominating part, it wouldn't contribute much to the limit. So sometimes the limit might work out much better. But again, sometimes direct comparison test works and the limit comparison test does not work. So be sure to try all and not both, of course. Anyway, as always, that's it.